welcoming Dr. Stephen Murray.
Today I'm going to give you sort of a snapshot of what we've learned about the inventory of the universe, what it's made up of, matter and energy.
My name is Steve Murray, and I'm the Deputy Director for Science at the Smithsonian Astrophysical Observatory.
When we look out in the universe, we use our eyes and we see normal matter. It gives off light and has gravity. We see ordinary stars and galaxies, and we see clusters of galaxies. These are the largest bound structures in the universe, hundreds or thousands of individual galaxies. But there's other material we see, other normal material, which is not in the same state as the matter in this room, but it's in the form of a hot plasma, and most of its energy comes out in X-rays, which is why we talk about how X-rays have an influence on our understanding of what's going on in the universe.
X-ray astronomy allows us to work in a part of the electromagnetic spectrum which is different than what we can see with our eyes. The visible part of the spectrum is a very narrow piece where we have electromagnetic radiation coming from radio all the way to gamma ray and X-rays. And so with X-ray astronomy, we look at these high energy part of the electromagnetic spectrum, and we see objects in a different light, literally. And we see things that are happening at higher energy. So we see what's happening at the atmospheres of stars, what's happening in galaxies, what's happening in clusters of galaxies that we wouldn't normally see with our ordinary vision.
It turns out that X-rays, when they strike a surface at a very shallow angle, will bounce off of it, just like a stone will skip on water. And so we can make X-ray mirrors by taking cylinders and shaping them just correctly into paraboloids and hyperboloids, and they'll focus X-rays down to a spot.
Well, the Chandra X-ray Observatory, of course, is a mission that is part of a sequence of what are called great observatories that NASA scheduled in the 1980s and 1990s.
How many of you have heard of the Hubble Space Telescope? Everybody? Yeah, I know. How many have ever heard of Chandra? Well, that's good. I'm glad to hear that.
Chandra is, in fact, the Hubble Space Telescope of X-ray astronomy. The wingspan is about 65 feet, and the length is about 45 feet, and weighs about 10,000 pounds. So the light from distant objects is focused by this X-ray telescope onto a bunch of digital cameras, instruments at the back, that take pictures of these X-ray sources, and then we send them back down to the ground. It was sponsored by NASA, and since it was launched in July 23rd of 1999, it's been operated at the Smithsonian Astrophysical Observatory, where we schedule observations, we carry them out, we collect the data, we process the data, and we hand it off to the scientists for analysis.
If you look at all these galaxies flying around in the middle of clusters of galaxies, they're moving very fast, 2 million miles an hour. And if they're moving that fast, they just ought to fly apart. And if you try to calculate how much gravitational force you need to hold them all together versus how much mass you see by counting up all the stars and galaxies, you fall short by about 10 to 20 times of what you need. So there was this problem called the missing mass problem. We didn't know in 1930 that it was dark missing mass, we just knew it was missing. Now comes the X-ray data. Now it shows that at least some part of that missing mass is due to this hot plasma that we can't see in visible light, but we can see in X-ray light. But when we add that up, it's still not enough. We're still short by factors of 5 or so, maybe even more. That's the real dark matter.
Dark matter is that part of matter which we don't see because of radiation. It just doesn't make any light at all, whether it's radio light or visible light or even X-ray light. It makes no radiation at all, but it does have gravity. And the forces of gravity are very important in shaping the way the universe behaves. It's gravity that holds our sun together. It's gravity that holds our Milky Way together. It's the gravity that holds clusters of galaxies together. And it turns out that dark matter is maybe 10 times more abundant than what we call normal matter. And the forces of that gravity, 10 times more powerful, have a very big influence in the way the universe is structured.
In the case of dark energy, we don't know much at all about it, excepting that its impact is to have this effect of anti-gravity. We don't know, for example, if it's constant over time or whether the magnitude of dark energy changes with time.
The Smithsonian Institution is probably known most as the museum on the mall, the collections that we contain. But what people probably don't realize is that another huge part of the Smithsonian is its role in the increase of knowledge as well as the diffusion of knowledge.
We don't know a lot, but we've learned a lot. We don't know every answer to all of our questions, but we have a bright future to think about what's coming next.
One of the best parts about being a Smithsonian scientist has been the freedom that I have to conduct the research that I'm interested in and to do it over a very long period of time. For example, it took almost 25 years from the inception of the idea of building the Chandra X-ray Observatory until it was actually launched.
Einstein told us everything that can be counted does not necessarily count. Everything that counts cannot necessarily be counted. We've now done our counting. We know what is. Now we have to understand why.
Carrying out these programs of research that I'm involved with involve a lot of different kinds of observations, collaborations with lots of different people, and again, the ability to do that at the Smithsonian is somewhat unique.
And with that, I'll thank you, and I'll leave the floor open for questions.